Let's start with today's topic, what actually we have delivered to you. In the very last class, we have just completed the closed packed structures. What actually the closed packed structure wants to define us, I have told you that just as we have uh, keep going from one dimensional to two dimensional to three dimensional structure, okay? And in this structure, we have told that in one dimension, we have just one particular way, that is this one. That means we have just one dimension, either it is x-axis or y-axis, and in which we have also defined that there is a particular uh, system known as the coordination number, or the number of coordination spheres, which actually tells us how many neighboring atom or molecules are joined with a particular atom. Okay, this was all about it. And then we have gone through the two dimension, in which we have studied that one dimension is just stacked over up and above to make its two dimension, like in x-axis as well as y-axis. That means vertically as well as horizontally. Okay, and in that case, we have studied, we have two different type of close packing. First one is square close packing, and second one is hexagonal close packing. Okay, in square close packing, we have described that there is AA type of structure in which there are total 4 number of coordination sphere which are attached to each other, whereas in hexagonal there is total 6 number of spheres which are closely packed to each other, and which is also known as octahedral close packing. Okay, in the very same way, we would move to our next topic, that is three-dimensional close packing, which is very same to two dimension. See, if we are going to make the simple concept, that is AA dimension, whenever we are going to repeat with AA dimension, let me write, this is our three dimension close packing. And I just wanted to say that whenever we are just going to move with AA dimension and I'm stacking over another layer over it, what would happen? Our simple unit cell would be formed. So in AA dimension, in AA type of two dimension close packing, if we just put another layer over it, if we try dimension, nothing would happen. We would just create our simple cubic unit cell. So that is very basic. Okay, in the very same way, just we have done with AA close packing, we can similarly move to our hexagonal close packing or AB type of close packing that we have just discovered in our last class, that what actually AA type and AB type wants to define us. Okay, AA type was square close packing, which on making with three dimension would give us a simple cubic unit cell. Whereas if I'm going to repeat with AB or hexagonal close packing, what would happen? See, it would seem little bit complex, but we have to make it understand that whenever we put a AB type of close packing and we want to put another layer of the same AB type over it so that it would make three dimension. But in the three dimension, it seems little bit difficult because here we have the length also, the breadth also, and the width also. Okay, so in three dimension, we have to, the whiteboard I am representing over here, it is just in two dimension. Okay, so it would be little bit difficult, so please try to understand what I actually want to say to you. Whenever we put another layer of the same AB over it, there would be formation of two type of voids known as tetrahedral and octahedral voids. There would be formation of voids. Now what actually void wants to define us? Void means there is a formation of space. There is a kind of little bit hole. There is a kind bit of space which is not occupied by any kind of atom. Okay, so this is AB, and I am just trying to put this AB again over it. Whenever I will do, there would be formation of tetrahedral void. First one known as tetrahedral void. In tetrahedral void, there would be formation of void, there would be formation of space when four number of spheres are closely packed to each other. They are placed over one and above to each other. See, making it the diagram would be little difficult as I have no more two more different colors. That would be much easier and nicer to explain. But I just want to make this concept over here that whenever we are trying to make, there would be formation of a tetrahedral, a kind of tetrahedral, like this way. This is known as tetrahedral void. There would be a sphere over here, over here, over here, and there would be a space left between them, which is known as tetrahedral void, which seems to be like this. Okay, so it seems to be a kind of tetrahedral with four different sides, as we have four different spheres connected to each other. Okay, this is same as it is. The tetrahedral void is present over the above surface, and in the below surface there would be formation of octahedral void somewhat over here. Okay, in octahedral void, there is also stacking, there is also formation of one layer over the other, and there is actually coordination number of 6, and that would behave like a diamond, like this we have, and another this would be like this. There would be something this known as octahedral void. Okay, this seems to be a little bit triangle type. Whenever we are putting first ring over the other, there would be formation of two triangle, one the same triangle and the other inverted triangle. It would be seen whenever you just go through your book. What happens actually when we try to put one layer over the other, the above layer makes the void known as tetrahedral void, which seems to be like this, and the very same way in the lower layer there is also a formation of space, there is also a formation of void known as octahedral void, which is formed due to connection of 6 closed spheres. Okay, that is known as octahedral void. The tetrahedral void is denoted by T and the octahedral void is denoted by O. You can see very closely in your notebook, which is explained with two different color diagrams. That would be easier for you to understand. That is a kind of concept which makes you clear that yes, there is formation of two type of voids known as tetrahedral and octahedral. As it seems so complex, but we have to read nothing about it. We just have to know that yes, how these two types of voids have been formed. But on the basis of these voids, on the basis of number of these voids, we have some numericals which are very important for your board exams. Okay, so on the basis of the number of tetrahedral voids, we have a simple mathematical formula on the basis of which we can derive the formula of the particular molecule. I'm repeating it again. On the basis of tetrahedral as well as octahedral void, we have a general formula, we have a general numerical formula on the basis of which we can deliver, we can convey what actually is the formula of that particular molecule. That means how the number of atoms are arranged, in which ratio they are arranged. That is known as the molecular formula. Okay, this is kind of somewhat you have read in chapter number 1 in 11th class, the empirical formula and the molecular formula. In the very same way, on the basis of these voids, we will calculate our molecular formula. Okay, so let's see how it happens. I hope I have tried to deliver you what actually tetrahedral and octahedral void wants to deliver you, what they want to express you. Okay, this seems to be a little bit difficult as to express in diagrammatically, but please try to share, try to tally this with your book, and please come to the point that what actually octahedral and tetrahedral voids are. After that, I'm going to move to our next topic, the numerical formulas. Okay, if you have still class when we finish our class. Okay, so let's move to our numerical formula. Okay, in the very same way, we have placed third layer over the second layer, but that would be very complex and that's not in your syllabus, so please leave this. Okay, now let's have a numerical formula, how we can deliver that, how can we make our formula of the compound. Okay, now on the basis of these tetrahedral and octahedral voids, we have to write the number of closed spheres. Okay, I'm just going to rub this octahedral and tetrahedral void. Okay, so he wants to say, let we have the number of closed spheres be n. Let the number of closed spheres be n, which are making over one over another by stacking over one over another the type of voids, that is tetrahedral as well as the octahedral voids. Okay, so the number of closed spheres be n. In that case, the number of octahedral voids would be always equal to the number of closed sphere, that is equals to n. If I'm saying that there is hexagonal close packing or cubic close packing, that would be also equals to n, because we have just tried to understand that this 3D generation, when octahedral voids are formed, this is only formed when we are putting our hexagonal close packing and we are taking another layer over this hexagonal close packing rather than the square close packing. Okay, same as it is, the number of octahedral voids be n, but the number of tetrahedral voids would be equal to 2n. This concept you have to remember, that if we are assuming our number of closed spheres be n, then octahedral voids would be n, but the tetrahedral void would be twice to the number of octahedral void, so it would be 2n. If we have remembered these two concepts, then it would be very easy for us to calculate the molecular formula. Let's see a numerical, very simple numerical. We have to calculate the formation, the formula of compound on the basis of number of voids we have. The question is, a compound is formed by two elements X and Y. The atoms of the elements Y is like an ion, they make cubic close packing. So we have X and Y is representing cubic close packing. And he's saying the X occupy the octahedral voids. Now we know very well that the octahedral voids is also equal to n. The cubic close packing, the hexagonal close packing, they also equal to n. That this is an n. So the ratio would be x1, y1, since we do not have any kind of variation. So the molecular formula would be x1, y1. This is that much easy. Okay, on the basis of just number of an octahedral void and tetrahedral void, in which we have just remembered this simple concept, we can easily score our 2 to 3 marks question in our board exam. That is too much easy. Just put over the number and calculate the ratio. On the basis of that ratio, we would derive that how can we calculate our molecular formula. Okay, this is so much easy. Same as it is, we will put another question in which we have octahedral as well as tetrahedral voids. Okay, so we have another question. The another question is, I'm going to rub this one. The atoms of element B forms hexagonal close packing. So the element of B has hexagonal close packing. hexagonal close packing equals to n, and element A occupy 2/3 of tetrahedral voids. Please keep in mind the question is saying to us that we are having 2/3 of tetrahedral voids, and the tetrahedral void represent 2n, that means 2/3 into 2n. Is it visible? I'll write over here. That means 2/3 into 2n. So we have a, B, A equals to 2 multiplied 2, 4/3n. B, we have just n. We would just cancel out n by n, and we have this formula. But since this is in fraction, and the atom and the number of molecules can never be in fraction, so what will we do? We will, by just cross multiplication, make it A4B3. And this is so easy. This is the answer that we can calculate our molecular formula. Okay, class, this is so simple, which was seeming so complex, that how we express our octahedral and tetrahedral void. But on the basis of calculating the number of octahedral and tetrahedral void, we can very easily calculate the molecular formula, like we have just done in this question and the previous one question. Okay, so please go through some more questions that are present in your textbook, in your in-text questions, and you will keep practicing. Your concept would be much stronger. Okay, so this was all about this topic. If you still have any kind of doubt, please ask to me. Please feel free. Okay, now what we have done, we have just delivered that we can make with the help of voids, we can make with the help of spheres on the basis of their interaction, on the basis of joining, we can make them close packing from one dimension to two dimensions. And on the basis of this, we have generated two type of voids, octahedral as well as tetrahedral. And after that, we have just done these numericals. Okay. Now, this was all about we have done. Till now, in the solid state, if I'm talking about your board exams, that how much score we can complete ourselves, or we can preserve ourselves for the solid state. See, our chemistry has been divided into three parts: physical, inorganic, and organic. And each part has its own importance. This is divided in three different marks, which is almost 23, 23, and 27. The 27 is for organic chemistry, 23 for inorganic, and 23 for physical. These we are going on with physical chemistry. In physical chemistry, we have 4 to 5 chapters, that is solid, solution, and electrochemistry, chemical kinetics, and surface chemistry, the 5 chapters. That means each chapter is almost related to 4 to 5 marks, almost 5 marks. Okay, so the solid state in your board exam would be of almost 5 marks, in which you would get the 2 marks question, which we have just done, and the 1 mark question would become from that particular table we have done in our 2 to 3 previous classes. That was, we have 7 different type of primitive unit cells. That was cubic, that was your octahedral or rhombohedral, and on the basis of the edge length as well as the axial angle, we have different type of primitive unit cell, and we have to calculate that how we have the edge length and the angle vary for each primitive cubic unit cell. Okay, so these within these 2 lectures, we have scored our complete 3 marks question. Okay, now we are left with our 2-3 topics, that is packing efficiency and the imperfection, and the last one is magnetic property. We are left with only 3 topics in the solid state. So now we're going to move with the packing efficiency. The packing efficiency is also based on table based, but we have some numerical derivation in which also. So first I am going to define you what actually packing efficiency wants to deliver you, and then we are going to, based on that packing efficiency, with our three different type of unit cells. That is our simple unit cell, our face centered unit cell, and the body centered unit cell. Okay, so let's move with the topic, which is packing efficiency. What packing efficiency wants to say? Okay, see class, the packing efficiency wants to say that how much efforts we can apply in our solids, how much efforts we will do to make them complete close packing, 3-dimension, 2-dimension, still there should over it. I'm saying, I'm repeating it over again. It's saying that how much efforts we can apply to make them closely packed, still there would be some space left over it. We have just seen that there is kind of tetrahedral void, octahedral void, or there is some kind of space, as I was trying to show you with the help of diagram. Okay, so the packing efficiency means our unit cells or our crystal lattice is how much percentage packed over. I'm again repeating, the packing efficiency is defined as the percentage by which our substance, our solid state, is completely packed without space. Suppose I'm assuming that our substance is 100%. We have the solid state with 100%, but there are space present over it. So we will see that from 100% is our substance 65%, 75% packed. That is known as packing efficiency. Okay, so you got the definition of packing efficiency. Packing efficiency is defined as the percentage of total space filled by the particles. Okay, so let's start. Now we have three different type of structures, which are the simple unit cell, the body center, and the face center. Let's start with simple unit cell. You know very well that in simple unit cell we have the atoms present only and only at the corners. Okay, so now we want to calculate that how much percentage is occupied when we are repeating the simple unit cell again and again. Okay, so with the help of numerical derivation, we're assuming that we have an edge length of A, and these are spheres. This dot represents our spheres or number of atoms, and we are assuming that we are having the edge length A. Now we are saying that each sphere or each atom, see class, as I have already told you that every unit cell has some edge length, some axial angle, and this lattice point, this dot actually represent the atom, the molecule, or the ion. That means this is constituent. This dot is actually a constituent present in that solid. Okay, so he wants to say that this dot represent atom, and we have just seen within our last two lecture that atoms are represented as spheres in chemistry. Okay, so we are saying that this is A and there are spheres present over here. So he wants to say, we have radius of this sphere equal to R. He's saying that there is radius R of that particular sphere. So we are having A equals to 2R according to the unit cell, according to the definition. On the edge length, we have only 2 spheres must be equal to 2R, because we have half of the sphere over here and half of the sphere over here. like this. This is A and this is R, this is R. So A equals to 2R. This is radius. अगर मैं इसको complete करूँगी, that would be our diameter. We are not talking about diameter, we are just talking about radius. So our A edge length would be equals to 2R. From here, we also calculate R equals to A by 2. Okay. Now, we know very well that in a simple cubic unit cell, the number of atoms present over here equals to 1. We know that now. In the last class, we have seen that the number of atoms present in a simple unit cell equals to 1. The number of atoms present in face-centered unit cell is equals to 4. And the number of atoms present in body-centered unit cell equals to 2. We have just gone through that numerical derivation. Okay. So, as we have the total number of atom equals to 1, so let me calculate volume of occupied space equals to. Now, since this is a sphere and we know very well, we are studying since our 7th to 8th class in mathematics, the volume of a sphere is equals to 4 by 3 pi r cube. You know that now very well. 4 by 3 pi r cube. And how many number of actual atoms we have? Only 1. So 1 into 4 by 3 pi r cube. Same as it is, we can calculate the volume of the complete unit cell. The volume of complete unit cell. And the simple unit cell represents like a cube. And what is the formula for the volume of cube? That is side multiply side multiply side. That is equals to A cube. And what is A? 2R cube. So we have two different type of volumes. Now the formula of packing efficiency, is equals to volume of one atom divided by volume of this complete cubic unit cell multiply 100. Yani we are doing just nothing. We are taking the small thing over the upper side and the larger thing over the lower side, just as we do in our simple mathematics. This is nothing. Okay. And we are multiplying it with 100 our percentage, because our packing efficiency would always be in percentage, as I have already told you. Okay. So what can we do now further? After putting this result, let me put this over here. Whenever I put this result, what would be the answer? The packing efficiency would be equal to, what is volume of one atom? 4 by 3 pi r cube divided by 2 r cube, that is 8 r cube multiply 100. Okay. And whenever we solve this r cube is cancelled. Whenever we will solve this complete formula, what would we get? We get pi by 6 into 100. And solving it, pi putting 22 by 7, what would we get? We would get 52.4%. This is the final result. Okay, this is the final result, class. So in short, we can say that in a simple unit cell, there is only 52% completely packed. Otherwise, there is a space present over there. Okay, so this was the packing efficiency, and this was the example of packing efficiency in simple unit cell. And class, you know very well that after 10 minutes, we have another class in which we will discuss the face center and the body center. So now tell me if you have any kind of doubt or something. Otherwise, we will discuss the doubts in the next class. All right, please ask any kind of doubt or query to me. You're allowed, students.